As we look at compositions of mixtures, we're going to use some of the same ideas we did when looking at our analysis of formulas, but we're going to try to understand it in terms of two different compounds instead of maybe two different elements. So as we look at rubbing alcohol here, that is a mixture that's 70% alcohol by mass. That means the other 30% is something else. In this case, we will know that that other 30% is water. You can make pure rubbing alcohol 90%, but most of what you buy at the store is 70%. So we take 25 grams of that. It is distilled, it is boiled. When you think distilled water, what happens there is we boil the water, water vapors collected, and then that pure water is what we use in our experiments. The leftover junk is what it was distilled away from. The 16.3 grams of distillate, the thing that boiled away, is collected. Which component, the water or the alcohol, is what boiled away? And what's the percent mass? So we're kind of trying to figure out, okay, 16 grams boiled, was that 16 grams the alcohol part or the water part? So we take the 16 over 25 times 100. We have 65.2% of distillate or of liquid that boiled. We subtract, we see we have 35% of the stuff that was left over, the solvent. Because almost 70% boiled away, it's probably the alcohol. One thing we could kind of think about with that is maybe we need to boil it a little bit longer to get a little bit more alcohol there, or maybe our sample isn't what it needs to be. So especially thinking about germs and viruses and getting rid of all of those, testing to make sure that your percentage of antiseptic is high enough is super important. That's why we want precise, repeatable data. We would do this, we might heat it up again or heat it a little bit longer and see what happens. B asks about water being hard. Hard water has a lot of calcium and magnesium, and in Indiana, we've got a lot of those things, especially calcium from the limestone. Water softeners replace those ions with sodium. So we do a reaction there. We're keeping the calcium and magnesium out of the water, putting the sodium in, because sodium does not form solids and doesn't make your cups in the dishwasher all cloudy and chalky, or you can see that in the beakers in the classroom. What's a good technique that would work for these things? So we had several different techniques. We could not filter this because these things are dissolved and this is also dissolved. Boiling it, well, the water would boil and everything else would stay behind. Chromatography, all of these are ions that would attract to things in fairly similar ways. So we're trying to think just different techniques here, and this is where selective reactions work. Calcium and magnesium do form precipitates, but sodium never does. Maybe you know or remember that from before, or maybe you've never heard that in your life. We will talk about that later in this unit in some videos, the how and the why of that. But the key idea there is we could get something that doesn't react with sodium, but does react with these. So we mix that chemical there, and then we filter it out. The magnesium and the calcium would be in the solid. They would be on the filter paper. The sodium would go through, and we could analyze to see, well, how much precipitate do we have on our unsoftened water? Maybe a lot. And then how much precipitate do we have in our softened water? And hopefully it's a lot less. And here, sodium chlorate, on our last example, reacts when heated to produce sodium chloride and oxygen. Describe an experiment to test the purity of that. So sodium chlorate is a white crystal powder solid. Sodium chloride has almost all of the same obvious physical properties. So what we would want to think about is, well, how could I know that it is this thing? If you've taken other AP science classes, there may have been whole questions where you're writing in detail every little step. In AP chemistry, there are far few questions where you are asked to write detailed step by step by step by step, earning tons of points problems. It's normally a part of a question worth it 2 or 3 points. But we do want to think about this. And by doing the labs in class, we will learn these. So what we would think about would be, if we had pure sodium chlorate, it would decrease in mass by a predictable amount. This has a mass. The final product of solid sodium chloride has a mass that we could know based on the ratio of those molar masses. Impure sodium chlorate, maybe it had sodium chloride mix in or potassium chlorate or any other element in there mixed with it, just some sand. It wouldn't decrease in that exact same ratio. The only thing that would decrease in this ratio is something that has the exact ratio of the mass of sodium chloride to the mass of sodium chlorate. So we would mass a sample of the sodium chlorate before we heat it and probably know the mass of the empty container or crucible. We'd heat it up, we'd mass it, we'd heat it again, and we'd mass it again. Kind of like the rubbing alcohol example I gave. Like maybe we just didn't react it far enough. We keep going to make sure that the reaction is totally done. We almost always go one more heating after we think that we're done to prove that we're done. If that mass stayed constant, if our answer for 3 and our answer for 5 were the same, that means we've heated it enough that the reaction's done. If not, we keep going until the mass stays constant. In terms of what we would have to record, we need to know how heavy is the crucible, how heavy is the crucible with the solid. We would then be able to figure out how much solid was there, but then after the heatings as well. An important step on a problem like this is it doesn't tell you or ask you about what calculations do you need to do. If it asks you what calculations would you do, you answer that. Otherwise, you just describe the experiment. A lot of people see a problem like this and then keep going and going and going, wasting their time talking about how to analyze the data. If they just want the experiment, just show the experiment.